Hey everyone, and welcome. Today, we're diving into a really cool communication method that, believe it or not, connects the world of hobbyist gadgets with the cutting edge of deep space exploration. It's called pulse position modulation, or PPM for short, and it's just a brilliant solution to a really fundamental engineering problem.
So let's start with a puzzle. What could NASA's super advanced deep space lasers and a simple toy drone possibly have in common? Seriously, think about it. It's not a trick question. The answer is this incredibly clever bit of engineering that solves a huge problem for both of them. How do you send a super clear signal without completely draining your battery? And that answer is PPM.
And this gets us right to the heart of a classic dilemma for engineers. It's kind of like, how do you shout to your friend across a really noisy room without completely losing your voice? In the world of electronics, that's the same thing as trying to send a signal through a noisy environment without killing your power source.
I mean, this is the eternal tug of war, right? On one hand, to make sure your signal is heard loud and clear over all the background static and interference, you have to pump a lot of power into it. But for something like a satellite or a drone that's running on a battery, every single drop of power is absolutely precious. So how do you do it? How do you get that crystal clear signal and a long battery life?
Well, this is where the genius solution comes in. What if, instead of just yelling louder, you could whisper, but with perfect, impeccable timing? That is the core idea behind PPM. You're not encoding information in how loud you are, but in precisely when you speak.
So let's define it. Pulse position modulation is all about timing. It's right there in the name. The information isn't in how strong the pulse is or how long it lasts. Nope, it's all about when that pulse arrives. The pulse itself is always exactly the same. The only thing that changes is its position in time. You can think of it like a metronome where the click always sounds the same, but the rhythm itself is carrying the message.
And this is where you can really see how clever PPM is, especially if you put it next to another method, something called pulse width modulation, or PWM. With PWM, you're changing how long the pulse lasts, like holding a flashlight beam on for a longer or shorter time to send a signal. But with PPM, the flash is always the exact same length. All you're changing is when you decide to flash it. It sounds like a really subtle difference, but it has absolutely huge implications.
And this quote right here, it nails the most important rule of PPM. The pulse itself never, ever changes. That's its superpower. Because the receiver isn't listening for how loud the pulse is, it's just looking for that specific, unchanging pulse to arrive at a certain time. This means it can ignore a ton of background noise that would totally mess up other kinds of signals. It's like listening for one specific, clear bell tone in the middle of a noisy train station.
Okay, so we've got the what. We understand the big idea. Now let's get into the how. How is a TPM signal actually created, and then how is it decoded on the other end? Let's pop the hood and look at the blueprint.
Making a PPM signal is this really elegant multi-step trick. You actually start by creating a PWM signal first. Remember, that's the one where the pulse width changes. Then, you use a special circuit that's basically like a starting gun. It watches that PWM pulse, and the instant that pulse ends, it fires off a brand new, perfectly standard-sized PPM pulse. So as the original PWM pulse gets wider or narrower, the starting gun fires a little later or a little earlier. You've cleverly translated a change in width into a change in position.
And to decode it, well, you pretty much just run that whole process in reverse. It's beautiful. A timer starts at a reference point, and then when the PPM pulse finally arrives, the timer stops. The length of time that the timer was running perfectly recreates the width of that original PWM pulse. From there, a simple filter smooths it all out, and boom, you've got your original signal back. It's just like measuring the time between the start and stop clicks on a stopwatch.
But as you know, in the world of engineering, there's no such thing as a free lunch. PPM is an amazing solution, but it's not perfect for every single situation. It comes with its own set of trade-offs. You get some incredible advantages, but you have to give some things up in return.
And these trade-offs are pretty significant. So on the plus side, you get fantastic noise immunity and incredible power efficiency. Huge wins. But the downsides? Well, you need a lot of bandwidth, a lot of space on the airwaves, because you need to be able to measure that timing with extreme precision. The clocks on the transmitter and receiver also have to be perfectly, and I mean perfectly synchronized. If their stopwatches are off, the whole thing just falls apart. And finally, in places where there are a lot of echoes, a reflected pulse can show up late and look just like a brand new signal, which, as you can imagine, can cause a lot of confusion.
So, keeping those strengths and weaknesses in mind, where does PPM actually get used? Let's take a look at some real-world applications where it's not just a good choice, it's the absolute perfect tool for the job.
Okay, so first up, if you've ever flown a hobby drone or an RC airplane, you've used PPM. It's the industry standard for sending a whole bunch of different commands, throttle, steering, pitch, roll, all of it, over a single radio channel. Each pulse's position in a repeating frame corresponds to a specific command, like moving a joystick. It's an incredibly efficient way to pack all that control data into one simple signal.
Now this is where PPM really, truly shines. NASA uses it for deep space communications with lasers. See, you can't just fire a high-powered laser continuously at full blast across millions of miles. It would overheat and destroy itself. PPM is the perfect solution. It allows NASA to send incredibly short, powerful bursts of light, packing in a ton of data and then letting the laser rest and cool down between pulses. It is the absolute pinnacle of power efficiency when you need it most.
And if that wasn't cool enough, check this out. PPM is also used to send data underwater. Water is a terrible medium for normal radio waves. They just don't go very far. So instead, engineers use beams of light, usually from blue or green lasers. And PPM is the perfect way to modulate that light, creating high-speed optical data links for things like submarines and underwater sensors, sending information through the water with tiny flashes of light.